Hello everyone, I'm Xingyu Zhou and I'm from Vanderbilt University. We are here to present our work of cost-effective hardware accelerator recommendation for edge computing. This work is done together with Robert Canady, Shunxing and instructed by Professor Andy Gokhale in our DocView group. So here is the outline for this presentation. We will first give a brief introduction to current stages of hardware accelerators in Edge, and then we will show some practical challenges for their practical deployment. And in order to solve these challenges, we develop a simple solution and use a case study to show the procedure of this solution. So the first question is, what are hardware accelerators? As their name indicates, hardware accelerators are hardware devices that can help accelerate computations. They could be general or specific for certain tasks. Of course, the hardware computation acceleration is compared to the most general form of CPU computations. So we could have the following paths for computation acceleration. We could choose stronger CPUs, or we can choose graphical processing unit of GPUs to use for better stream processing. Or in the past 30 years, field programmable gate arrays, FPGAs, have shown their power in the digital signal processing field. Or further step, we could use ASICs, which stands for application-specific integrated circuits, for certain tasks. So why do we really need this kind of acceleration hardware on the edge? The reason is actually quite simple, because we are facing more and more higher and higher computation burdens on the edge. We are facing more heterogeneous data sources from multiple kinds of sensors, especially those kind of cameras that will involving multiple kinds of image or video streams, and also for the for many applications on the edge that will involve some realistic physical constraints like the power and physical size or many other aspects. So based on the following situation we have mentioned, we have seen the current challenge of the overall practical deployment for this kind of acceleration hardware. That is, we do have many different hardware choices. However, the current evaluation and benchmarking selection research are either focused on one single type of device, or they are more focused on even lower level of circuit design direction. So we have to face the dilemma that we still need to understand the applicability of this kind of accelerators for more at-scale and edge-based applications. So in order to measure the quality of the acceleration, we need to choose some metrics. So based on the literature we have followed so far, we choose the following three: latency and power and commercial cost, which we believe to be the most practical and most commonly used. So how to define an overall hardware acceleration strategy? We believe a hardware acceleration strategy actually consists of two aspects. The first aspect is how to realize the tasks on a certain type of device. That is, what hardware device you are choosing and what task you choose to compute on them. And second aspect is the placement of the device. That is, what location do you choose to place the hardware in the design topology, and also how many the time and deployment cycle you plan to use it. So overall, we believe a good hardware acceleration selection can be formulated as an optimization problem to minimize the overall cost under some certain design constraints. So here we actually formulate an optimization problem to minimize the cost, which is the sum of the hardware cost and the electricity long-term cost, under the constraint that the computation acceleration can make the computation latency short enough. So in order to solve such an optimization problem, we present a cost evaluation workflow consisting of several steps. The first step, of course, is we need to make a choose application for the in the design topology that needs to be accelerated. So with the emergence, and the popularity of current deep learning, we choose two quite popular computation burdensome tasks which the first one is a classification task using the ResNet50 neural network, and the second is the vehicle detection task using the tiny YOLO neural network. So having choose the task, we need to go through hardware configurations and realize them using their specific design flows. So we need to point out that the diversity of the design flows really varies for the different hardware devices. And in practice, this seems to be quite obvious burdensome for this kind of hardware accelerator deployment. And after we have realized and validated that this computation task can really be working correctly on a certain type hardware, we do a per device benchmarking and record their time and power traces. And in the next step, we incorporate this measured traces data and use them to do the overall system level cost evaluation. So in summary, we present such a evaluation workflow from the topology design, extraction, and the device, and extend the performance evaluation from single device level to the overall metrics approximation. So this expands the pattern from single device to the overall system level. So here's the result for our per device validation. We choose some relative high dimension data to guarantee their lower level dimension compatibility. So we choose some image recognition and also the road vehicle detection data that are relative high dimensional and measure their time and power traces using some certain instruments and denote them as random variables to approximate and denote their computation power. So based on the power and time traces, we incorporate them into the design application topology of the system level. So here we choose a quite typical 3-level design topology layout, from the cloud to the and then the intermediate level of fog, and then consisting of the lowest level of edge nodes connecting directly to the camera sensors. So we set as overall system reliability level as the for groups. We need them all 3 groups to be working, and each group at least 2 out of 4 cameras should be the camera nodes data should be handled handled correctly at a certain confidence level. And so based on this kind of reliability-driven ideology, we can compute the system-level computation or reliability with a confidence level. And also, we set the burdens on input nodes with an intermediate level of complexity. That is we set the standard deviation and equals to the mean value of the input here, and use a random variable to denote computation burdens. In order to approximate the design latency constraint, we choose the latency information flow from edge to cloud. That is, we define such a latency as the information latency flow from edge to fog and then fog to cloud. And we assume that the communication bandwidth between both these two using as the standard Wi-Fi bandwidth. And we get the latency approximation results for each inference information flow cycle for each tasks. And based on all these methods discussed above, we set an overall deployment cycle of 24 months and estimate their overall deployment cost for different hardware for 2 tasks. And from this approximation results, we can actually draw some important conclusions from different aspects. We first show why hardware accelerators are really necessary, because general CPUs really show the least cost efficient and worst performance overall. And also we show why power is critical in the long-term deployment. And in this long term, we believe FPGAs and embedded GPUs show the highest potential. We also need to point out some potential trade-offs for different devices, such as even though FPGAs are good performance, they really have a very high usage threshold. And also, even though NCS are really easy to use plugins, they only have very limited computation power, something like this. So in summary, our paper presents a simple evaluation procedure that can serve as a recommendation system to help users select an accelerator hardware device for their edge application scenarios that can cross the pattern. So as this is a very preliminary level of work, we admit that there are still much things to be done, and there are current many limitations, such as we only consider a pure strategy consisting of one single type of device involving one single type of task need to be accelerated. And also, we only consider an ideal task scheduling and device parallelism. We didn't really consider the interference effects between devices and communications. So that's all for now. Thank you, and questions are welcome.